So why exactly have I done all this trash? You might ask this yourself. Good morning, fellow mathematicians. Welcome back to another video. This one might look quite weird on the first sight, just because it is. We're going to integrate the Bessel function of the first kind of the zeroth order today, from 0 to infinity, improper BOI, some infinity BOI right here. And if you have never heard of this function before, it's just a solution to a differential equation. And yeah, it looks like this right here. It looks absolutely fucking horrible. And we are going to try to make a little bit more sense of this right here. If you've ever dealt with quantum optics or wave mechanics, you might have encountered this thing right here. It's one of those special functions that you maybe might encounter in your lifetime, or maybe you don't. And it really doesn't quite matter. It really doesn't add anything to your life or to your lifespan. It's just a pretty sexy looking boy right here with factorials here, a gamma function, all an alternating series. Oh, I'm going to come. Yeah. Okay, let's go ahead and get started. I don't want to deal with this zeroth order right here at the moment. I just want to try to make a little bit more sense of this mess right here. And let's go ahead and get started, and let's disassemble this a little bit. Okay, so you see we have this t over 2 to the nth power term, and well, our sum is independent of n, so let's bring this term to the outside. So at first we have t to the nth power over 2 to the nth power times. A lot of trash, a lot of trash. We have this gamma function right here, and I want you guys to remember one little property of the gamma function. If we have gamma of n plus 1, well, we can interpret this as n factorial. That's just by definition how it is. But what is n factorial? Well, n factorial is nothing but n times n minus 1 factorial. But by this definition, so you see gamma of n plus 1 has been n factorial. So gamma of n is nothing but n minus 1 factorial. So it's recursively defined. It's just how it is. So this right here is nothing but n times gamma of n. Okay? Keep this property in mind. We are going to use it extensively now. Okay, at first we have, well, this is negative 1 to the 0th power, so this is just positive. Then we have over 0 factorial. Okay, over 0 factorial, this is just 1. Here we have 2 to the this chunk to the 2 times 0, so this is just 1 overall, this is just to the 0th power. And then we have 1 over gamma of, okay, k equals to 0, this is just gamma of n plus 1. Okay, next term is going to be negative, it's an alternating series. Up here we are going to have, well, how should I put it? Yeah, t over 2, okay, to the 2nd power squared. Over, okay, this is giving us 1 factorial, this is just 1, so let's get rid of that. And this is gamma of n plus 2 in the end. Okay, just going to write it out, and we are going to see how we can turn this around a little bit using this definition right here. Then for the next term, I'm going to write out 2 more terms, and then we are going to see what we are going to get. This is now t over 2 to the, okay, 4th power right here. We are just going to get even terms all the time on here. Over, okay, k factorial is going to give us 2 factorial. Then we have gamma of n plus 3. I hope you can already see a certain pattern here. So next term is going to be negative. Up here we are going to have t over 2 to the, okay, this is going to give us 6th power. Over 6th power. Then we have 3 factorial right here. And this is gamma of n plus 4. Plus infinitely more terms. Okay, this is already quite a mess, and let's see if we can make any sense of it. What about gamma of n plus 2? Well, by this definition it's going to be n plus 1 times gamma of n plus 1. Familiar term? Gamma of n plus 1? Okay, so you see? Gamma of n plus 3, just on this one right here. It's going to give us n plus 2, then times n plus 1, and then gamma of n plus 1. Okay, and on this last term, for example, maybe you have already guessed that this is nothing but n plus 3 times n plus 2 times n plus 1 times gamma of n plus 1. This is looking ugly as hell. This is more of a weird looking S of 5. Okay, so you see we have this gamma of n plus 1 as a common term. So let's bring this to the outside. So we have t to the nth power over 2 to the nth power. Then we have gamma of n plus 1 times. Okay, this first term is just 1. On this next term we have negative t squared over 2 squared. And then times, I'm going to put it here still, 1 factorial n plus 1. Okay, does it even matter? No, it doesn't matter if I have 1 factorial here. Actually, that's why I got rid of this right here. Okay, then we have plus t to the 4th power over, okay, this is going to give us 2 to the 4th power, 2 factorial, n plus 2 times n plus 1. And for the last one, just writing it out a little bit more, negative t to the 6th power over, okay, then we have 2 to the 6th power 3 factorial, then we have n plus 3, n plus 2, n plus 1, plus dot dot dot, okay? This is what we have right now. This is a long derivation. I'm just rewriting everything now, so it's not too hard actually. Okay, what I want to do is I want to distribute a 2 into here, for example. So this is going to give us, okay, let's write everything out once again, t to the nth power over 2 to the nth power, gamma of n plus 1. Okay, then we have 1 minus 2 squared over 2 times n plus 2, 2n plus 2 actually, if we distribute 1, 2 into here. Then we have plus 2 t to the 4th power over. Okay, let's distribute this 2 factorial being nothing but 2 into here and another 2 into here. Okay, then we have 2 to the 3rd power times 2n plus 4 times 2n plus 2. Okay, I'm doing this on purpose. But what is 2 to the 3rd power? This is 2 times 4. So 2 times 2 squared is 2 times 4. Okay? Now for the last term, we are going to get negative t to the 6th power over. Okay, if we distribute 1, 2 into here, 1, 2 into here, 1, 2 into here, then we get 2 to the 3rd power, then we have 3 factorial, and then we have 2n plus 6, 2n plus 4, 2n plus 2, plus dot dot dot. 3 factorial is nothing but 6. 2 to the 3rd power is nothing but 2 times 4. Okay? And so on. So we have infinitely more terms, but maybe you can already see a pattern. So what we have here is this coefficient right here. Also, the highest number that you get down here in the denominator is going to be plus this thing right here and also our exponent. So we have the highest number down here in the denominator is the 4. So we get 4 right here. Also we have this 2 right here on this term. So it's kind of repeating, you could say, and then we have a 4 as the highest power. Just for the last term, so we have 2, 4 and 6 here, so 6, 4 and 2, and also 6 is the highest number, so it's going to be our exponent. We have derived this, and after deriving this whole chunk, we can actually take a look at our Bessel function, zeroth order, first kind. Let's erase this and let's do it on next blackboard. So why exactly have I done all this trash? You might ask this yourself. So this has been the Bessel function of the nth order. Why not plug a 0 into our very n everywhere and see what we get? So if we plug a 0 into here, that's just 1 over 1, and well, this is gamma of 1, it's 0 factorial, it's just going to be 1. Okay, so this whole chunk is going to be 1. Then we have, okay, j0 of t being nothing but, okay, we have a 1 and a negative, okay, t squared over, this is going to be 0 on this term, so we have 2 times 2 is going to give us 2 squared, positive. Then we have t to the 4th power over, this is 0, so we have 4 squared times 2 squared. On the next term we have negative t to the 6th power over, and you might guess it already, 2 squared times 4 squared times 6 squared. You could go on with this process, so t to the 8th power over 2 squared, 4 squared, 6 squared, 8 squared, negative dot dot dot. So this right here is our Bessel boy at the moment. how can we continue now? So yeah, you could solve this step by step, but you won't really get something nice, so you won't see at first sight what this is going to evaluate to. You are going to get an ugly looking infinite series, and it's not going to be any fun. So we are going to do something nice. Now we are going to use Laplace transforms. My most favorite tool. You see, I'm losing my mind already. So why not take a look at Laplace transform of, well, J0 with respect to t. Our Laplace transform is going to be with respect to s. You see, then we can just take Laplace transform on all those terms, but it's defined as an integral, so our Laplace transform is linear. I've made videos on that. Take a look in my Laplace transform playlist to get a hang on all those details I'm using here. So, okay, taking the Laplace transform of 1 is going to give us just 1 over s. It's just how it is. Also, if we have the Laplace transform of t to the nth power, it's going to give us, yeah, this is nothing but n factorial over s to the n plus 1th power. I have derived this right here when I derived my gamma function. So I've derived the gamma function using Laplace transforms and Feynman integration. You should take a look at this video. Maybe it's up here. So that was quite amazing. It was so good. It was such a nice derivation. I'm so proud of myself. Okay. So 1 over 2 squared, and this negative 1 is just a constant, so we can bring it to the outside of Laplace transform. So this is 1 over 2 squared, negative 1 over 2 squared at that. Then we have t squared, okay? By this formula it's going to give us 2 factorial over s to the 2 plus 1, okay? Power, I'm going to put it like this. Then we are going to get, okay, this is just 1 over 2 squared times 4 squared, and then we are going to have, well, 4 factorial over s to the 4 plus 1 power. Let's do one more iteration. Then we have negative. Okay, then we have 1 over 2 squared, 4 squared, 6 squared, and then we have 6 factorial over s to the 6th power plus 1 power. Yeah, and then plus dot dot dot, infinitely many more terms. It really doesn't quite matter. Okay, this is what we have now, and let's make a little bit more sense of that. I've put it like this, with this plus 1 up here in the exponent, because we actually have a common factor, 1 over s right here. So this is nothing but 1 over s times. Then we have 1 minus 1 over 2 squared, 2 factorial over s squared. Okay, plus, next one is going to be 1 over 2 squared, 4 squared, 4 factorial over s to the 4th power. Negative 1 over 2 squared, 4 squared, 6 squared, 6 factorial over s to the 6th power, dot dot dot. Let's rewrite this a little bit more actually. This is nothing but 1 over s times 1 minus, okay, this is 2 factorial over 2 squared. This is 1 over s squared to the 1st power. I'm going to put it like this, okay? Okay, just follow along, okay? Do not rush. Plus, okay, we have 4 factorial over 2 squared, 4 squared, and then we have nothing but 1 over s squared squared. Next term, negative. Okay, then we have 1 over 2 squared, 4 squared, 6 squared. Instead of a 1, I'm going to put 6 factorial up here. And then we have 1 over s to the 3rd power squared plus dot dot dot. Why have I done all this? Why the fuck would Daddy make something like this? It's actually quite easy. I'm doing most of the stuff on this channel for a certain purpose, and when I derived the Taylor series expansion of square root 1 plus x, I also did its little brother, the Taylor series expansion of 1 over square root 1 plus x. And what you can witness here, just try it out for yourself. Take a look at this video I once did. It's not too long ago when I did it. This right here is nothing but, well, the Taylor series expansion of the square root of, well, the Taylor series expansion of 1 over square root of 1 plus 1 over s squared. So replacing this as our x and then going through the whole Taylor series expansion process, you're going to note that this indeed holds. This is nothing but 1 over square root 1 plus 1 over s squared. So much talking, I'm terribly sorry. That's a lot of stuff I have to do here. You see, you can just rewrite all those factorials a little bit and then you can bring it into the proper form that we have derived in this video before. So overall, our Bessel function, the Laplace transform, let's put it that way, it's nothing but 1 over s times this chunk. What else can we do? Well, we can factor out a 1 over s squared on the square root. So we are going to get 1 over s times 1 over square root 1 over s squared is nothing but 1 over s. Okay, then we have the square root of, okay, to get rid of this 1 over s squared term, to get back to our 1, we need an s squared term right here, plus 1. Okay, but 1 over s over 1 over s is just going to be 1. Why is this actually useful? So let's gather what we have right here, okay? Let's put everything here. So we have on the one hand that our Laplace transform of the Bessel function, zeroth order, is nothing but 1 over square root s squared plus 1. On the other hand, we have a different definition of our Laplace transform right here. Namely, that this is the improper integral from 0 to infinity of, well, our time-dependent function times e to the negative st integrated with respect to t. And we are going to play engineer from this point on, so we can't really say QED. We have to say, yeah, approximately instead of QED. What happens if we let our s go to 0 in this case, or even 0 plus? We are going to approach it from the top, you could say. Well, our integrand is strictly positive right here, so you see our factorial is going to grow extremely hard on this one right here, or those powers. So this right here is going to be strictly positive. This is our highest term, and then everything else is going to be less and less. So this is positive. This is also going to be completely positive all the time on this interval. Yeah, so our whole integrand is positive, meaning that we can use Fubini's theorem, if I remember correctly. I try to make sense of this function analysis or anal free stuff, those theorems. Okay, so our integrand should be strictly positive. That's why we can interchange limits. So if we take the limit as s approaches 0 plus, we can direct the limit to the inside. E to the 0th power is just going to be 1. So this is going to be our desired integral in the end. And well, yeah, a fraction is just, if the limits exist, then we can just bring those limits to each part. Our square root is indeed continuous, so we can bring this limit to the inside. This is going to be the square root of 1, so this is just 1. Okay, so meaning we have taken the limit on both sides due to continuity on here and due to our Fubini's theorem, the integrand being strictly positive, we can actually take the limit as s approaches 0 plus, and then we are done. So once again, a crazy looking integral has been evaluated to just 1. It is how it is, my boy. So this thing is actually equivalent to our integral from negative pi to pi of the Dirichlet or Fayet kernel. I wanted to say Ficher, but his name is Fayet. Thank you guys for watching. If you did enjoy this video, please like, subscribe, make a comment channel, or if you like. There was quite some work once again. I'm terribly sorry. Whew, this is so exhausting. If you film 4 or 5 videos one after another, you're just going to get rid of your lifespan, at least part of it. Never mind, I love making videos for you guys. Don't forget to support the channel in many ways by those teachers I created. Support the website. Take a look at the website. Go to the subreddit, support channel on Patreon. Never mind. I'm wishing you guys a flammable day, and yeah, if you did enjoy this video, please share it everywhere you can. Show it to your mother, show it to your dog, show it to your window. Maybe it's interested in it. Now, until the next video, have a Bessel day, I would say. See ya.
Guck mal, Akiro, hier ist ein YouTube-Tutorial, wie man mit Ballons spielt. Prima, siehst du? Bumm! Ugh.